As 2013 began, the central regions of the United States were not experiencing an ordinary winter from a meteorological perspective. The area known as Tornado Alley was showing unusually volatile atmospheric conditions. The winter months had been wetter than normal and warm. Moisture-laden air masses from the Gulf of Mexico were reaching inland regions earlier than expected. When this moisture combined with cold air circulating in the upper atmosphere, it created the fundamental ingredients required for severe storms. Meteorologists had long known that such early season instabilities often lay the groundwork for far more destructive events. Later in the spring, during the first months of 2013, the jet stream behaved in an atypical manner. Normally positioned farther north, this powerful ribbon of wind dipped unusually deep into the central United States. This shift significantly increased wind shear. Of the most critical ingredients for the formation of supercell storms, wind shear refers to the difference in wind speed and direction between surface-level winds and those higher in the atmosphere. As this difference increases, the likelihood of rotating storm systems rises sharply. In 2013, these values exceeded historical averages across many regions. As spring approached, moist air transported from the Gulf of Mexico spread across Oklahoma, Kansas, and Texas. Surface temperatures rose rapidly, while cold air persisted in the upper atmosphere. This vertical temperature contrast pushed atmospheric instability to extreme levels. Meteorological measurements showed CAPE values convective available, potential energy reaching dangerous thresholds in many areas. This was a clear indication that storms could develop explosively and with great intensity. In February, an EF4 tornado struck Hattiesburg, Mississippi, serving as the first serious warning of what the season might bring. The tornado tore through densely populated areas, flattening structures within seconds. Although no fatalities occurred, experts described the event as the product of perfect conditions. Effective warning systems and timely evacuations prevented a greater disaster. Yet this apparent success masked the scale of the danger that was still building. Throughout March and April, tornado activity increased steadily across the central United States. Texas, Kansas, and Oklahoma recorded numerous, moderate to strong tornadoes. These events indicated that the energy stored in the atmosphere had not yet been released. Meteorologists were now focused on a single question: when and where would this energy finally be unleashed? By early May, the central United States had entered an extremely fragile meteorological balance. Cool, upper-level air masses from winter lingered, while summer-like temperatures dominated at the surface. The boundary between these opposing air masses formed an invisible tension line stretching across Tornado Alley. On meteorological maps, this boundary appeared as a clearly defined dry line to separation between dry and moist air. East of the dry line, humidity surged. West of it, hot and dry air prevailed. Storms developing along this line are historically responsible for the most violent tornadoes. In May 2013, the dry line remained nearly stationary for days. This allowed energy to accumulate, stretching the atmosphere like a tightly wound spring. On May 15, 2013, a powerful tornado struck Granbury, Texas. EF4 level winds devastated the Rancho Brazos neighborhood, claiming 6 lives. Just days later, another tornado developed near Russell, Kansas. Radar data showed that supercells were becoming increasingly organized and intense. Meteorological services began avoiding the phrase routine storm. These tornadoes were not isolated incidents, they were precursors to a much larger atmospheric release. On May 20, 2013, Moore, Oklahoma once again entered history. An EF5 tornado with winds exceeding 210 miles per hour obliterated residential areas. The tornado remained on the ground for nearly 39 minutes, carving a destruction path 17 miles long. 24 people were killed, including 7 elementary school children. The destruction of Plaza Towers Elementary School became one of the most haunting symbols of the disaster. For Moore's residents, it was a devastating sense of déjà vu. In 1999, the same area had been struck by another EF5 tornado. 14 years later, the risk remained unchanged. This tornado occurred just 11 days before Reno. The atmosphere was still not finished. Following the Moore disaster, meteorologists found no relief in the model's only deeper concern. Surface moisture reached record levels, upper-level winds strengthened further, and wind shear approached near-perfect conditions for tornado formation. CAPE values climbed beyond 4,000 J per kilogram in some regions, signaling explosive storm potential. Helicity values also surged, nearly guaranteeing rotating storm structures. Experts now knew one thing for certain: another tornado was coming, and it would be different. The morning of May 31, 2013, was eerily calm across Oklahoma. Skies were mostly clear. Winds were light. The air felt oppressively warm. Experienced meteorologists know these are the most dangerous days. By midday, the Storm Prediction Center issued an outlook approaching the high-risk category. Officially, tornado probability stood at 15%, but the underlying atmospheric signals were severe. Western Oklahoma, particularly the area around El Reno, had become a magnet for supercell development. As the clock approached 3 p.m., storm cells began forming west of Oklahoma City near Weatherford and Clinton. Towering cumulus clouds rapidly evolved into rotating supercells. Radar imagery revealed distinct rotation. Hook echoes formed, mesocyclones intensified. The atmosphere had crossed a point of no return. That at 3:30 p.m., the Storm Prediction Center issued a PDS particularly dangerous situation tornado watch-in extremely rare. Designation reserved for the most severe scenarios. The question was no longer if, but where and when. By 4 p.m., one southern supercell became dominant, absorbing surrounding energy. This pattern is a hallmark of long-lived violent tornadoes. The storm began organizing southwest of El Reno. Visually, it appeared as a massive structure concealed behind heavy rainfall element that would later prove deadly. At 5:53 p.m., the first official tornado warning was issued, and just 10 minutes later, at 6:03 p.m., a tornado touched down approximately 12 kilometers southwest of El Reno. Initially appearing as a narrow funnel, it expanded rapidly but not in a conventional way. Instead of growing outward from a single core, it generated multiple sub-vortices orbiting a massive circulation. These sub-vortices moved independently, changed direction abruptly, and would become the defining feature of the El Reno tornado. Within minutes, the tornado spanned kilometers. Because it merged with rain curtains, its true size was nearly impossible to perceive visually. The El Reno tornado did not present a classic, sharply defined wedge. It was wrapped in rain, creating a lethal illusion of distance. Many believed the tornado was far away. In reality, they were already inside it. Sub-vortices flung outward at extreme speeds, with localized winds reaching nearly 300 miles per hour. These secondary circulations caused devastation. Independently of the main funnel, this was one of the most complex tornado structures ever documented. El Reno defied expectations not only in size, but in movement. Most tornadoes travel northeast. El Reno shifted southeast, then east, then back north. This unpredictable motion caught both the public and professionals off guard. The tornado behaved as though it were testing its surroundings. Such movement complexity is rarely observed in meteorological records. The tornado moved across wide agricultural fields near El Reno areas that appeared safer due to sparse development. But on that day, they were not empty. Researchers, media crews, storm chasers, and spectators had flooded the region. Roads were narrow, muddy, and visibility was poor. The tornado's true position was unclear. Disaster was inevitable. What truly set El Reno apart was its swarm of powerful sub-vortices. Some moved independently, others rotated in reverse relative to the parent circulation. Radar and damage analysis showed several of these sub-vortices were as strong as standalone tornadoes, with EF4, EF5 wind speeds. They were fast, they were unpredictable, they were invisible in rain. El Reno was no longer a single tornado, it was a system. The University of Oklahoma's Roxball Mobile Doppler radar captured the tornado at unprecedented proximity. Around 6:30 p.m., it recorded wind speeds of 135 to 150 meters per second, equivalent to 313 miles per hour, the highest ever measured in a tornado. These readings occurred only a few hundred meters above ground, confirming EF5 level intensity. The realization was clear. El Reno was rated EF3, not because it was weak, but because it missed major structures. The enhanced Fujita scale relies solely on damage assessment. Radar, data, and wind measurements do not factor into official ratings. El Reno was extraordinarily powerful, but it passed primarily through rural areas. As a result, it remained officially classified as EF3, a decision that sparked widespread debate and reshaped future evaluation methods. At its peak, El Reno reached 2.6 miles, 4.2 kilometers wide, the widest tornado ever recorded. But this was not a single visible funnel. The danger zone extended far beyond what the eye could see. Many entered the circulation believing they were safe. They were not. Forward speeds exceeded 55 miles per hour. Muddy roads, headwinds, and near-zero visibility made escape nearly impossible. The wind field extended 5 kilometers from the center. Vehicles were overturned without ever encountering the main funnel. The TwistX team was conducting scientific research, placing probes to gather data, but El Reno was unlike anything they had faced before. A sudden directional shift and aggressive subvortices eliminated escape options. Tim Samaras Paul, Samaras Carl Youngware, killed. For the first time in history, professional tornado researchers lost their lives in a direct strike. After 6:28 p.m., the tornado turned toward western Oklahoma City. Traffic was gridlocked. Meteorologists later estimated that a direct hit could have killed over 500 people. At the last moment, the tornado veered northeast. Disaster was narrowly avoided. After nearly 40 minutes on the ground, atmospheric support weakened. Wind shear declined. The storm shifted north. Cold air cut off the inflow. By 6:43 p.m., the circulation collapsed. The tornado vanished into rain. Officially: 8 Fatalities 300 plus injured, but El Reno impact cannot be measured in statistics. It changed science. El Reno exposed critical gaps in understanding. Invisible. With limitations of damage-based ratings, storm behavior radar technology improved. Public warnings evolved. Vehicle escape strategies were evaluated. The lesson was costly. After the storm, silent. Fields destroyed vehicle structures, but above all uncertainty, because what people saw was never the full picture. Experience was no longer enough. Distance was no longer safety. El Reno reshaped risk perception forever. This documentary is not only about whether it is about those who went out for knowledge, those who pushed limits, those who did not return. Some storms leave more than damage. They leave names. El Reno was not just a weather event. What spun in the sky that day was not only wind. It was uncertainty, the boundary of human knowledge and nature, reminding us that it is still larger than us. Danger does not always announce itself. Sometimes it arrives quietly, and when it is noticed, it is already too close. El Reno did not just take lives. It left questions. Science advanced. Systems changed. Rules were rewritten. But every step forward came with a cost. When El Reno is remembered, one question remains. Does knowing more always mean being safer? Nature does not answer. It does not explain. It simply happens, and humans understand only afterward. El Reno ended, but its mark remains, not in forecasts, but in memory, because some storms pass, but their lessons remain. This documentary was created not to frighten, but to remind. If this story made you reflect on our fragility in the face of nature, don't forget to like the video, subscribe to the channel, and follow for more documentaries. In the next episode, we will remember another forgotten truth.